Greetings, traveler. I'm the calculus cleric, and today we're working with infinite series. So, a specific problem is to calculate the total area of the infinitely many triangles below. Now, this problem requires more creative thinking than usual because there's no dead giveaways on what this may be. So, first, let's break this up. So, calculate the total area. So, we're finding the area of all these triangles below, and there's an infinite number of them. So that's probably what that dot 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 represents. It's another triangle, and these triangles get indefinitely smaller and smaller and smaller and smaller. So eventually it'll just look like a blue blob like that as they get really, really, really small. So we have to calculate the total area of these infinite triangles, which is typically what we use a series for. Now, an infinite series is exactly just this: numbers that will eventually get so small that they'll eventually sum up to something. These triangles look like they're doing the same thing. So, area. Let's start with that. The area of a regular triangle is half base times height. But as we can see from this graph they're giving us, that appears that all the triangles have the exact same height. That makes it a lot easier for us because now we don't have two variables but only one. So we'll substitute h is equal to 1/2 into the area equation, giving us 1/4 b. Okay, now we have base left, the b value. Let's go analyze what b is. So as we notice, the base is continuously changing. It does not remain the same. It gets smaller and smaller and smaller. So now here's the second thing we're going to do. Let's see if we can identify a pattern, because this is a series, and because it's a series, it will probably have some kind of pattern. If you notice, this distance is half, this distance is 1/4, this distance is 1/8, and so on and so forth. And so is there a pattern to that? Well, if we look at it more closely, this distance is a half, 1/4 is half of 1/2, and so on. 1/8 is half of 1/4, and we can keep repeating this over and over and over. So that's our pattern. It is something to do with 1/2. So you could say that the pattern looks something like this as we increase our n value, what we start at, and then say our second triangle is 2 and so forth. You can say 1, starting at 1 is 1/2. That's the distance of our base. Because the base is not like the numbers, we're looking at the distance between the two. Keep that in mind. And then second one is 1/4 and 1/8 and so on. But this doesn't really give us a good series to work with because then you just have 1 over 8n, which is not an evaluatable series. Because if we remember properly, when we take the series of, let's just start at 1 and factor out the 1/8, and then we have 1 over n. 1 over n diverges by the pure series rule, so this will not work. We need to find a different pattern. Well, 2 is convenient because we can also do this and get the exact same answer. Because if I increase this by 1, it's 1/2. Square 2, 1/4, a cube that, a 1/8, and so on and so forth. So this works as a fine substitution to our base as well. And this will also be more useful in the long run because not only will this not diverge, it'll also give us something called a geometric series. Now, this geometric series won't diverge because it's our value. First, the format of geometric series. This is the basic format of a geometric series, as the c value is a constant of some sort, and the r value is what is being exponentized. Probably a new word that I made up. Anyways, if that r value is less than 1, then the said series will converge. So evaluating this, what is the answer? Well, if we take an infinite series of this and we start at to determine whether we start at 1 or 0, I'm going to evaluate the area of the first triangle. If the area of the first triangle comes out to 1/4, then n starts at 0. If it comes out to 1/8, then n starts at 1. So that the base is 1/2, base times height. Height is also 1/2, so that's 1/4 multiplied by 1/2 equals 1/8. Okay, so the area of the first triangle is 1/8, meaning that our sum will start at n is equal to 1, and plug in the series onto the inside. Because this is a geometric series, there's a certain formula to evaluate that, which is this is the basic formula for a geometric series that does not start at n is equal to 0. So now this m variable over here is just simply what n is starting at. So we're starting at 1, so our m will be equal to 1. And our c value, we already established that. Our c value is 1/4, and our r value is 1/2. So now we substitute all these numbers into this formula for our geometric series, and it will give us that this series is equal to 1/4 multiplied by 1/2 all to the 1 minus 1/2. Right, and simplifying this out will lead us to get 1/2 to the 1 is just 1/2. So 1/2, 1 by 1/4 is 1/8, all over 1 minus 1/2, which is 1/2. Simplifying this leads to 1/8 multiplied by 2, which is 2/8, which is simplifying that is 1/4. The area of all these triangles will eventually sum up to 1/4.